This video is going to be about the idea of a sampling distribution. This is one of the more difficult concepts in the world of statistics. So I'm going to take a little bit to kind of recap the dichotomy, if you will, between the population and the sample in the world of statistics. And following that same dichotomy, we have the parameter and statistics. And following the same dichotomy between the population and the sample and the parameter and statistic, we have the distribution and the density plot or histogram. And further, we've started stretching this into random variables and observations. Observations actually showed up for us pretty quick on the sample side of things, like those are the data you observe, but we've extended this idea of random variable, and I'm going to try to lay that into the framework of the dichotomy between the population and sample. So after a recap of basically everything this class is trying to do, we will then move on to defining the sampling distribution. And then I'm going to tell you about the one theorem in the world of statistics that basically keeps me employed. It's called the Central Limite Theorem, and it relates directly to the sampling distribution. So then in R, following the definition of the sampling distribution, we'll try to do an example where we see sampling distributions and central limit theorems in the most tangible way I know how to get you to see. I'm putting the word see in quotes because it really is an abstract concept, and generally you don't see, in quotes, the sampling distribution in the applied world of statistics. This is just something like $1 million. I've never seen a briefcase full of $1 million, but I'm sure there exists a briefcase full of $1 million. That's kind of how you have to imagine the sampling distribution. This thing exists even if you can't touch it immediately. So let's dive into our recap so we can get this video moving on. We have in the world of statistics a population that is this large group of things we want to make statements about. Generally, though, the population is a little bit intangible, generally a lot of it intangible. And so what we do instead is take a random sample from the population such that we try to make statements about the population using only the information contained in the sample. So that is, we're trying to make statements about population parameters. So these parameters, alliteratively enough, population parameters, live on the population side. The parameters are the characteristics of the population that we want to know. We want to know things about the population mean of dogs' weights in the US. I don't know, I'm making it up. And in order to estimate population parameters, we calculate statistics. That is, our statistics, like the sample mean or the sample median, are estimating the population mean or the population median. And the way we have this in the world of statistics is we assume there is a population distribution. That is, we assume the population follows some shape that we call a distribution. And the population has a parameter like a population mean. And so when we sample a bunch of data from the population, we estimate the population mean with the sample mean, mu hat. Mu hat is our best guess of the population mean. Now, really, we get the sample mean from a bunch of data. And I'm going to write them as like little x1, little x2, all the way up to little xn, as if to say we have observations of x1, x2, all the way up to xn. And I'm trying to write those as little x's, as is standard in the world of statistics. But the way we get those observed values is through random variables. And random variables exist on the population side. That is, there are quantities that tell us about the shape of the population Theoretically, there are abstract quantities that tell us about the shape of the population and will eventually turn into observations. Once we measure the thing or record the thing or weigh the thing, those random variables, these abstract quantities on the population, will turn into observations. Those abstract quantities are our random variables that contain information about the population distribution. So this dichotomy that I'm emphasizing in the world of statistics is really about the distinction between the population and the sample. We want to know things, specifically we want to understand and know parameters, characteristics of the population, that are described by distributions of the population thing of interest, whatever it might be, heights of people, weights of dog, fat content of dolphin, I don't know. And the way we learn about the population is by theorizing. There are random variables that contain information about the distribution and the parameters of interest. And we sample those random variables to get observed values. The observations, the little x1, x2, all the way up to xn, are the values we add up all together and divide by however many there are so that we can calculate the sample mean, mu hat, in order to estimate the population parameters. Okay, that was our recap. The weird thing in the world of statistics is the idea of a sampling distribution. A sampling distribution is the idea that if you consider only the population side with the random variables, then those random variables have outcomes you don't yet know. That's what it means to be a random variable. So there are abstract quantities, x1, capital X1 through capital Xn. We don't know yet what values those are, but theoretically, they are mathematical objects. So you can take mathematical objects and you can add them together, all of them together, and you can divide by however many there are. And if you were to go out and do that, say this is our first theoretical sample, then we would theoretically get an estimate, mu hat, of the population mean. So I'm going to index mu hat with this subscript 1 to remind us that in the world of sampling distributions, we are considering random variables that could be sampled multiple times. So theoretically then, I could go out and I could get my own random variables. And you know what we should do? To help you recognize that these random variables are different than your random variables, we should index these twice. So this is for the first sample from you. That's your first observed value from your sample. And for me, let's try to clear this up a little bit. This is my first observed random variable for the second sample. And this is the nth random variable for the second sample. So we could theoretically add all those together and divide by however many there are, but I'm going to claim there's the same number of random variables in the second could have happened set of random variables. And theoretically, this could happen, let's say capital R times, where somebody could theoretically go out there and get the first random variable of the rth sample and all the way up to the nth random variable of the rth sample. And from this, you could calculate the rth sample mean. Now, the idea of the sampling distribution is that because all of these are random variables, and all of these are random variables, and all of these are random variables, that means these are random variables. Because if we don't know what values the random variables take on, that's what it means to be a random variable, then we don't know what values mu hat 1, mu hat 2, mu hat r will take on. We don't know what values any of these mu hats will take on because they are composed of random variables. That's this weird concept that you have to abstract the mean, what you used to think was like a single number, as if you just took one set of data, added them all up, and divided by however many there are. We want you to think of the sample mean itself now as a random variable that could theoretically be sampled from the population in an infinite number of different ways. So if you think of these mu hats as being an infinite number of possible sample means, each one of which is estimating the population mean, then the collection of sample means is going to make up for us the sampling distribution of the sample mean. And theoretically, there is a shape to the distribution that describes the idea that theoretically you could go out and take your own set of random variables and get your own sample mean. I could go out and take from the same population with the same number of observations my own set of random variables, and I could get my own mean. And it would be different from yours because of random sampling. And all the way down to the rth person, the rth person could go to the same population and take out their own sample of the same size and get their own sample mean. And theoretically, an infinite number of people could, in the abstraction, go to the same population and take out a same number of random variables from the population. And they could get their own sample mean. I know this never actually happens, but this is the way we think of the sampling distribution of the sample mean. If you take that collection of random variables that are the mean and you make a density plot of them, you will get the sampling distribution. And it has some shape. That collection of random variables that are the means has some shape. Okay, that was almost as particular as I can make it. Let's try one more idea. The sampling distribution is not just one quantity. There is, in fact, a sampling distribution of any statistic. That is, a statistic is just a function applied to some sample. That is, you could, like we just did on the previous page, add up all the numbers and divide by however many there are. That's what defines the mean. You could, to get a different statistic, sort all the numbers and pick out the middle one. That would define the median, which is to say, there exists a sampling distribution, this idea that if you and let's say capital R of your friends went out and each took your own sample from some population, and you each calculated your own median, and then as a collection of medians, plural medians, many medians, and you looked at the shape of those many medians, that would be a sampling distribution for the sample median. Okay, let's try again. There exists a sampling distribution as if you and all of your friends plus an infinite number more went out and took from the same population your own random samples, and each of you calculated the standard deviation. Let's call it sigma hat 1. And then this is you and your capital R friends each took your own random sample, and each of you calculated your own sample standard deviation. The collection of sample standard deviations has a shape. I don't really know what shape it's going to be, so I'm going to make it up. The tough part about the sampling distribution is a sampling distribution exists for every unique population, for every unique statistic, and for every unique sample size. All three of those things define one new sampling distribution. The real tough part is, in general, for an arbitrary statistic, we don't know what distribution. Let's make this statement a little bit easier. We don't know what shape the sampling distribution of that statistic for that population will take on. In general, we can't say what the shape of the arbitrary sampling distribution for a particular statistic is. That's a really tough idea in this world of statistics. That theoretically, you and your capital R friends could go out there and get your own random sample. And if each of you calculated your own statistic, that collection of statistics will have a shape, but we don't necessarily know what shape it is. There's only generally in one case, oops, sorry, that's some math I was doing earlier on my own. There is in general only one scenario where we understand well what shape the sampling distribution will take on. The Central Limite Theorem tells us the shape of the sampling distribution for specifically the sample mean. It does not necessarily tell us the shape of the sampling distribution for, let's say, the interquartile range. The Central Limite Theorem tells us specifically the shape of the sampling distribution for the sample mean. And specifically, it says, we always call it the CLT, says under some general conditions, which are very easily met, and I'm even just going to skip them now. But you should recognize that there are some conditions on that. We will talk about them later in this class. The sampling distribution of the sample mean is approximately normal. That is to say, the sampling distribution of the sample mean is nearly the shape of the normal distribution when the sample size is large. And that's a little bit more vague than you want it to be. What really happens is, as the sample size increases, the sampling distribution of the sample mean is increasingly normal. That is, as your sample size gets larger, the more normal the sampling distribution is going to look. Only in this specific case do we understand the shape of the sampling distribution. Only for the sample mean do we understand the shape of the sampling distribution. The crazy part about the central limit theorem, I know it's hard for you to understand that there's a crazy part yet, but I'm going to try to show you with some examples in R. The crazy part about the central limit theorem is that it doesn't care what the shape of the population is. The population could be right skewed or left skewed or unimodal or bimodal. As long as the sample size increases, the shape of the sampling distribution for the sample mean will be approximately normal. Let's see if we can convince ourselves of this using some simple, I hope, R code, because we've kind of seen it before, with some particular examples. So let's just remind ourselves that we can generate 11 Bernoulli observations with probability of, I don't know, I'm going to make it up, 0.66. So there is 11 observations where each observation can only take on the value 1 or 0, and there's a 66% chance that any observation takes on the value 1. Okay, so theoretically, we could replicate this code such that we have, let's say, 50 friends. Whoa, we have 50 friends that each of us took a sample of size 11. Here's the 46th friend who took a sample of size 11, and they observed, let's see, only 2 zeros, so 9 ones and 2 zeros. And here is the 50th friend who observed 11 Bernoulli observations. So we can take that code and store it into a variable x. Now, if you recall, when I looked at the 11 observations for each friend of ours, I was looking at the columns, which means we could calculate multiple mu hats by taking the column means of that variable x. So mu hats, let's just look at the first 6 of them. Here are the first 6 theoretical, like they could happen, even though this is not really how applied statistics works. You only ever take one sample. But theoretically, you could take 50 different samples of size 11 each. And from each one, you could calculate a sample mean. And here is the second of the theoretically possible sample means. Happens to be equal to the first. That's pretty rare, but maybe because our sample is so small. Here's the third of the possible sample means. Here's the 5th and 6th of the possible sample means from the Bernoulli distribution with a true population parameter p equal to 0.66. Notice if we changed that population parameter, our sample means would change because they'd be estimating a different population parameter. In the end, we would get a different collection of mu hats and then get a different sampling distribution. Let's extend this idea to, let's just say we're going to have 1,001 friends, and we're going to take a sample of size, let's start at 50. And then we'll put the sample means into a data frame. And then using the library ggplot, this is the closest we can get to visualizing. Okay, so here it is. Here is the data frame named df, and in it, it contains a column mu hats, from which I want to make a density plot. Now notice how pretty much that density plot looks approximately normal. Okay, maybe there's a little wiggle in the shoulders, but in general, that looks unimodal, symmetric, and centered basically at the true population parameter 0.66. Now, the crazy thing is, if we take an increasingly big sample, and we'll update our data frame, and then update our plot, the plot should look more normal. That's the part of the central limit theorem that says as long as you're calculating means, as your sample size goes up, not the number of friends you have, but as the sample size goes up, the sampling distribution for the sample mean will look increasingly normal. This is a crazy idea because it doesn't matter what population distribution you're looking at. For instance, here's a new distribution that you don't have to understand too much about. It's named the exponential distribution, and you can randomly generate observations from the exponential distribution with the function REXP. And let's say we want 10 of them with whatever this population parameter named rate is, and we'll specify it equal to 3. The exponential distribution takes on only positive values. And in fact, it is right skewed. For instance, if you do a quick example where we create a data frame of, let's say, 1001 randomly generated observations from the exponential distribution, to prove to you that the exponential distribution is right skewed, let's look at the density plot for the exponential, for 1001 exponential observations. So there is a right skewed distribution. If we repeatedly sample from that distribution, let's say we have 1001 friends, each of whom is going to randomly sample 301 exponential observations with rate parameter equal to 3, I don't know. And then if you create a new data frame where you look at the sample means, which I'm going to call mu hats, from all of your friends' observed values, I ask you as a task to include in your course notes. Complete this exercise as we have done earlier in the example. We did it previously with the Bernoulli distribution. Now I'm asking you to do this with the exponential distribution, which I'm clearly showing you here to be right skewed. I want you to use this new data frame to make a plot of the sampling distribution of the sample means from the exponential distribution. And I'd like you to tell me what shape the sampling distribution of the sample means takes on, where it looks like it's centered. And if you really need a guess of where it's centered, you can just look at all these values of mu hats. And then tell me what kind of shape the sampling distribution of the sample means takes on from the exponential distribution. And tell me why. What theorem tells us the shape of the sampling distribution of sample means, no matter how right skewed or left skewed the population distribution is. Please include this please finish this example in your course notes and include a description of the sampling distribution and an explanation of why the sampling distribution looks the way it does. What theorem tells us this much?